Building a custom home on Earth is a massive logistical headache. Now, imagine trying to pour a foundation in a total vacuum, where the temperature swings 300 degrees between blistering heat and a deep freeze. For years, NASA's plan was to avoid building on the surface immediately, opting instead for a massive orbital waiting room, a space station called Gateway that would circle the moon. But to accelerate the Artemis program, they've benched that idea. They are heading straight for the dirt. The new blueprint is a $30 billion three-phase push. It starts with an armada of robotic landers, delivering heavy machinery and rovers, laying the groundwork for a fully operational permanent crewed outpost in the 2030s. This map shows their exact target, the moon's south pole. It is heavily cratered and treacherous, but those deep, permanently shadowed areas hold ancient water ice, the key to producing drinking water and rocket fuel on site. Skipping the orbital station cuts overhead and puts habitats on the ground much faster, but it also forces engineers to immediately confront three compounding hazards that make the lunar surface one of the most hostile environments humans have ever faced. The first major hazard is simply keeping the lights on. Once the permanent Phase 3 base is up and running, the supply chain math becomes brutal. This data visualization shows what it takes to sustain that lunar outpost. NASA estimates they will need 38 tons of materials shipped from Earth every single year just for basic maintenance. That requires a continuous heavy freight pipeline stretching 384,000 kilometers into the void. Getting all that cargo safely to the dirt relies on a highly fragile architecture. NASA's Orion spacecraft has to launch from Earth and execute a flawless docking procedure with commercial landers waiting in lunar orbit. These commercial systems, like the Blue Moon lander shown here, are massive engineering undertakings. However, the commercial lander programs are currently facing severe schedule delays, putting the entire timeline at risk. Every single ounce matters. If this precarious, multi-stage supply chain breaks down anywhere along the line, the lunar base fails before the astronauts even unpack. Even if the logistics hold up, the physical topography of the South Pole is actively trying to destroy human hardware. This cross-section of a South Pole crater maps out the thermal extremes. At the bottom, temperatures plunge to negative 334 degrees Fahrenheit, far colder than any temperature recorded on Earth. Yet nearby sunlit peaks bake at 130 degrees. But severe temperature swings are secondary to the ultimate physical enemy of lunar exploration, a powdery substance called lunar regolith, or moon dust. Without wind or water to wear them down, billions of years of meteorite impacts have crushed the rock into tiny, razor-sharp shards of glass. Solar static makes this dust cling stubbornly to spacesuits, seals, and electronics. It degrades equipment with terrifying speed. Every routine surface walk turns into a race against material wear and mechanical failure. The hardware, though, might outlast the humans. The third and final hazard is the severe breakdown of human physiology in deep space. All life on our planet evolved inside a specific gravity and magnetic field, an adaptive metabolic envelope that our biology requires to function correctly. This report from the Gaia Foundation highlights a significant physiological risk. Their research into quantum biology suggests that stepping outside Earth's protective envelope triggers a rapid systemic decline in cellular function. Astronauts experience accelerated bone density loss, failing retinal function, and unshielded ionizing radiation bombarding their DNA over long stays. NASA can build the rockets and the metallic habitats, but if they cannot engineer medical solutions to this biological breakdown, humans will never be able to permanently occupy the base. This classic Apollo-era image represents a moment of triumph, but today the concept of a brief, symbolic lunar visit is obsolete. Today, the central question driving the Artemis program is whether the United States can return astronauts to the lunar surface before China does. This Chinese rocket model represents a competing national architecture. Arriving first is a hollow victory if China follows up with a more stable, expandable, and repeatable base. The true metric of victory in the 21st century space race is sustained access. It requires an unbroken logistics chain, durable surface infrastructure, and genuine operational continuity. The Moon's south pole is humanity's ultimate survival laboratory. Conquering its logistics, dust, and biology is the mandatory prerequisite for our eventual leap to Mars.